Okay, in our first part of chapter 4, we're going to revisit the exponential function and introduce the logarithm function. All right, so the exponential function, as a reminder, if we write our z as x plus iy, this is e to the x cosine y plus I times e to the x sine y. In particular, the real part here is e to the x cosine y, and the imaginary part is e to the x sine y. And the claim is this is entire, so it's analytic on all of z, or holomorphic on all of z. And so let's check that. So let's check the Cauchy-Riemann equations. All right, so ux is the derivative of this guy with respect to x. We're just going to get e to the x cosine y. And uy is supposed to be the derivative with respect to y. We're going to get e to the x times the derivative of cosine, which is negative sine. Now Vx is e to the x sine y, because the derivative of the exponential function is itself and for real numbers. And Vy is e to the x cosine y. And in particular, the partial derivatives ux and vy are equal, and the partial derivatives uy and vx are equal and opposite. So the Cauchy-Riemann equations hold. In fact, they hold everywhere. So e to the z is analytic. Well, entire. Let's be more precise here. It's analytic everywhere, so it's entire. Furthermore, we can detect its derivative from this. So remember that f prime of z we can think about in two ways. One of the ways is ux plus I bx, from back when we proved the Cauchy-Riemann equations. And so in this case, ux is e to the x cosine y, and vx is e to the x sine y. But this is exactly what the exponential function is. So we recover the fact that the derivative of the exponential function is itself, we extend the fact that the derivative exponential function is itself to all of complex numbers.